Hello. Okay, this lesson is about logarithmic functions, graphing them, transforming the graphs. We're going to do both exponential and logarithmic functions. We're going to describe the changes, the effects of the graph if we change the coefficients and the exponents of them. So you can perform the same transformations on exponential functions that you performed on polynomials, quadratics, and linear functions. So that means that the same things that you learned before also apply now. We learned before about the transformations of this function. We know that the 2 in front is a vertical stretch of 2, and that the inside here, this affects the x values. We have a translation 3 units to the right, and that the negative 4 moves it down 4. And then a negative in front of the x here is a reflection. This is a reflection across the y-axis. And then we have it's being moved up 1. So those same things affect exponential functions. And for example, let's take the function y equals 2 to the x. If we add something on the outside of the function, that's our vertical translation. So it's going to either move it up if we add a positive 3 like this, or down. It'll move it down if we have a negative 6. If we add to the x value, and the x value is the exponent. So if you look at the exponent and you see something added or subtracted, that is our horizontal translation. And remember, the x values are opposites. So if we have subtracting 2, that moves it 2 to the right, and adding moves it to the left. Multiplying in front of the function is our vertical stretch or compression. So when we multiply the function here by 6, that's our stretch of 6, and multiplying by 1/2 is our compression of 1/2. If we multiply inside the function where the x is, then we're going to have our horizontal stretch or compression. So if you look up at the exponent and we have something multiplied, that's going to be our stretch. Now remember, the x values are opposite. So even though this looks like we're dividing by 5, that's a stretch of 5. And multiplying by 3 is a compression of 3. Then we have our reflections. If we have a negative, the negative outside the function affects the y values, and that is a reflection across the x-axis. And a negative inside the function next to the x affects the x values, making the x values negative is a reflection across the y-axis. Let's look at an example. Let's see if we can make a table of values and graph this function g of x. We can describe the asymptote and then tell how the graph has changed from the original function. So first of all, if I take I can just make a t-table of values here and plug into the function g of x. If I plug in negative 3 into this function for x, I would have 2 to the negative 3. That turns to plus 3, so 2 to the 3 is 8. Plus 1 is 9, and I can see I have all these values. I could have also gotten them by plugging into my calculator. And you can't see the graph. Okay, I'm going to keep going. The asymptote, you can't see the graph. Okay, so we can plot these points, and when we plot them, we're going to get the function here, the red one. Okay, that red function has been changed. I also graphed the original function, the blue one. Okay, so as you can see, the asymptote, it used to get closer and closer to the blue function, comes down closer and closer and closer to the y-axis right here at 0. But then since the function has been moved up 1, okay, the asymptote is right at y equals 1. The transformation reflects the graph across the y-axis and moves it up 1. Okay, let's see if we can graph this function, find the y-intercept and the asymptotes. Describe how the graph is transformed from the original function. So, first of all, the parent function for this would be 1.5 to the x. Okay, so whatever the exponential is the parent function. Okay, now we can see that it's been multiplied by the 2/3 in front. If we want to find the y-intercept, we can plug in and find the value when x is 0. So if we plug in x is 0 into the function, we get 2/3, because 1.5 to the 0 is just 1. And so the y-intercept is 2/3. The asymptote is the same as the parent functions because it's not moving. Okay, so let's look at the graph. Okay, so when you look at the graph, you can see that it didn't actually move, so the asymptote is still right here at y equals 0. So the graph is a vertical compression of the parent function by a factor of 2/3. Because a log is an exponent, transformations of logarithm functions are similar to transformations of exponential functions. You can stretch, reflect, and translate the graph of the parent logarithmic function the same as exponentials. And so here are the transformations for exponentials. They are, or for logarithms. It's the same as for exponentials and the same as for quadratics, really. So here you can see the difference between taking between adding outside the function, which affects the y's, the vertical, and adding inside the function, inside the logarithm, which is a horizontal. And the difference between multiplying outside the function and multiplying inside the function with the x. So good. Graph each logarithmic function. Find the asymptote. Describe the transformations. Okay, so first of all, what is the parent function? Okay, the parent function here is log of x. The asymptote for log of x is just at x equals 0. Okay. The graph, let's see if we can see the graph. Okay. The graph, so when we graph it, that's how you can tell where the asymptote is, by when you graph it, you can see that the asymptote here is right at x equals 0, right on the y-axis. And the graph is, the 5 in front is a stretch. So we have a vertical stretch of 5, and then the -2 is a shift. It's been translated 2 units down. Okay. Let's see if we can now write our transformation if they tell us how to change it. So if we take this original parent function, x to the 4 to the x, and we reflect it across both axes and move it down 2 units, what will our new function be? Well, we know that reflecting it across the axis is a negative in front of the function. Okay, begin with the parent function. To reflect across the y-axis, we're going to put a negative in front of the x. And to reflect across the x-axis, we need to put a negative in front of the whole function. Then to move the function 2 down, we have to subtract 2 from the function. So here is our new function, g of x. Okay, let's do the same thing, but this time with a log. Let's say the log is compressed horizontally by a factor of 1/2 and move 3 units left. Okay, compressed horizontally is going to affect the x values on the inside. And they're going to be opposites. So if we're compressing by a factor of 1/2, we're going to have to multiply by 2. And then if we're moving 3 units to the left, so that's also to the x value, we have to add 3 to the x. When you write a transform function, you may want to graph it as a check. And we can graph it and see that, yes, it moved 3 units over and that it's also been stretched horizontally. Or let's say compressed actually horizontally. Okay. A group of students retake the written exam portion of a driver's test after several months without reviewing the material. A model used by psychologists describes the retention of the material by this function, a of t, where a is the average score at time t, which is measured in months. Describe how the model is transformed from its parent function. When would the average scores drop below 0? And is that answer in fact reasonable? So first let's understand the problem. What they're looking for here is a description of the transformations, and they want us to solve for time when the function is 0. They give us this formula, okay, and we know that from this formula that the parent function we're talking about is log t. Okay, so what we're going to do is we're going to rewrite the function in a more familiar form, use what we know about the effects of changing the parent function to describe the transformations, and then we're going to also have to substitute at to equal 0 and then solve for the unknown in the function. So first let's rewrite the function and describe the transformation. So as far as rewriting the function, let's just move the 85 to the other side, so that, because usually the k value is added or subtracted off of the end of the function. Okay, so we can describe the transformations. The graph is reflected because it has a negative right here. We have a reflection across the x-axis. It's been multiplied by 15, so that's going to be a vertical stretch of 15. It's going to be translated 1 unit to the left. That's what this plus 1 will do. And then moving it 85 units up. Now find the time when the average score drops to 0. So we're going to set the function equal to 0 and then solve. So subtract 85 to the other side, divide by 15, by negative 15, and now we can rewrite the log in exponential form. Okay, and when we evaluate that, we get t equals 464,000. Wow, okay, and this is measured in months. Okay, this is a lot of months for the retention to drop to 0. So actually, okay, so change the months to years. We're talking about 38, 39 years here for the retention to drop to 0. That is unreasonable. It is unreasonable that the scores would drop to 0 38,000 years after the student has taken the test without reviewing the material. All right, good. Yeah, so there's an applied example of that for us, and that is it.